Proszę, proszę. So, welcome all. TCS seminar at Jagiellonian University. Today our speaker is Bartosz Walczak, a local colleague, PhD in computer science, 2012, expert in structural graph theory, graph colorings. Bartek does some discrete geometry. He likes algorithms very much. I don't know if you do some of those these days, less. It's a pleasure to have you here, Bartek. The floor is yours.
Yes, thank you. So what I'm going to present is joint work with Tara Abrishami, Marcin Briański, James Davis, Seymour, Jana Masarzykowa, Piotr Paweł Żążewski, yes, and myself. So this will be an extended version of a talk which I already gave at Beers this year. I will try to show more of the actual proofs and the proof methods which are used for this result. But for the first half of my talk, I will be quite closely follow what I was already talking about at Beers. Okay, so the first part of my talk will be related to Scott's conjecture. Before formulating the conjecture, and let me give you this definition that a class of graphs G is chi-bounded if there is a function with the property that for every graph in the class, the chromatic number of the graph is bounded from above by that function of the clique number. So I'm going to use standard notation, the Greek letter chi for the chromatic number of the graph, omega for the clique number, which is the maximum size of a clique in the graph. And we know that the class of all graphs is not chi-bounded because there are graphs with arbitrarily large chromatic number and with no triangles. Therefore, it makes sense to speak about chi-bounded classes of graphs because for a class of graphs, may either allow these kind of constructions or not. So the research about chi-bounded classes of graphs, we can say that some kind of systematic research was initiated by Garfash in the 80s. In particular, a fundamental problem is what kind of structures we can exclude as induced subgraphs so that the class of graph that is obtained after excluding these structures becomes chi-bounded. Yes? So here we have this very famous Garfash-Sumner conjecture. Garfash 78 and independently Sumner conjecture that I guess in 81, that for every forest F, the class of F3 graphs is chi-bounded. So whenever I'm speaking about F3 graphs or something free, it will mean that we exclude this F as an induced subgraph. Okay, so this is excluding as an induced subgraph. We know that it is not enough to exclude any graph, any specific graph which contains a cycle, because there exist graphs with arbitrarily large chromatic number and arbitrarily high girth. Therefore, forests is like most that we can expect for this kind of statement. And this conjecture is still considered to be widely open. It was proved for specific cases such as paths or graphs with radius at most, like trees with radius at most 2. And there are many other special cases like this, but in general, it is considered wide open. However, in the 90s, Alex Scott proved a statement which is very analogous to this one, except that we not only exclude this forest as an induced subgraph, but we also exclude all subdivisions of these forests as induced subgraphs. Subdivisions means that, okay, we take some tree, for example, like this one, but we are allowed to put additional vertices on the edges, and we don't want to see anything like that as an induced subgraph. Okay? So he proved this statement, and there was also this famous conjecture which is now known to be true, famous conjecture by Diarfas that if we exclude cycles of at least some length as induced subgraphs, then the class becomes chi-bounded. And excluding cycles of at least some length is equivalent to excluding induced subdivisions of a fixed cycle. So Scott, like generalizing these two statements, like his theorem and that Diarfas's conjecture, he suggested that the following can be true. That for every graph F, not necessarily forest, just any graph, the class of F subdivision free graphs is a chi-bounded. However, this conjecture turned out to be false. So for some graphs F which contain a cycle, necessarily because of this conjecture, which is still not known to be false, disproving this for a forest. Okay, this cannot be disproved for a forest because of Scott's theorem, but for graphs, some graphs containing a cycle, this turns out to be false. Okay, so there is a specific class of graphs which satisfies this condition that it is F subdivision free for some F. And this class of graphs is important in the literature on its own. They are called string graphs. So string graphs are intersection graphs of curves in the plane. So we have some, let me maybe draw it here, we have some family of curves in the plane, and what we do, we introduce a vertex for every curve, and we put an edge whenever such two curves intersect. So here we would have this, this, and perhaps this as edges. Okay? So there is an observation by Zinden in one of the earliest papers about string graphs that for every graph F which is a one subdivision of some non-planar graph, let me maybe use a very specific example, like for instance K331 subdivision, which means that we take K33 and we introduce one additional vertex on every edge. This is K331. So for this kind of graphs, the class of string graphs is free of induced subdivisions of them. Okay, so string graphs exclude induced subdivisions of, say, K3, 3, 1. So in particular, for string graphs are F subdivision free for some F. Yes. So a specific case of this conjecture is that the class of string graphs is chi-bounded. This was actually conjectured before by Kratochwil and Neshetwil. And that turns out to be false as well because of the following construction. So there is a class of graphs defined by Burling in 65. And Burling defined a class of graphs, let us denote these class of graphs by B1, B2, and so on, with the properties that these graphs are triangle free. They have large chromatic number, so say the chromatic number of BK is equal to K plus 1. And they are representable as intersection graphs of three-dimensional boxes. So that was the original purpose of this Burling construction. This doesn't yet imply anything about string graphs. However, in 2014, in a group of people, Pawlik, Kozik, Krawczyk, Lasson, Micek, Trotter, and myself, we proved that these Burling graphs, they are actually string graphs. Okay, so the graphs B1, B2, and so on are string graphs. So this implies that the class of string graphs is not chi-bounded because of these properties, and therefore, as a consequence, Scott's conjecture is false. However, up until now, this Burling's constructions is still the only one known to falsify, known to disprove Scott's conjecture. So one could, it just might be a coincidence, but maybe it is not. Okay, so yes, so one could think of the following way of saving Scott's conjecture. That where does the notion of chi-boundedness come from? It comes from the fact that if the chromatic number is large, then we want to have a bounded size witness that it is large. Maybe not as large as we started from, but we want the witness which has bounded size and still large chromatic number. Okay? A clique is a good witness with that property. But such a graph as BK is also a good witness with that property. It has bounded size. I didn't show you yet the construction of Burling, but I will do it later during the course of my talk. But it will be a specific graph, so it has bounded size, and it has large chromatic number. Okay, so let me now introduce this definition that a class of graphs G is B-bounded if there is a function f, say a function with two parameters, such that for every graph G in the class, the chromatic number of G is bounded by that function, first of the clique number, but also as the second parameter, we take the maximum size of a Burling graph contained in that graph as an induced subgraph. Okay, so we take the maximum K with the property that that BK is an induced subgraph. Of G. Okay. So think for a moment. Think of this these Burling graphs as just some construction of triangle-free graphs that with high chromatic number that you know of, maybe Michelski graphs or maybe shift graphs or maybe whatever. There are plenty of such constructions, and they are very specific constructions. So, like at first sight, this definition might look very strange. Like, why would we want to find, like, to have a bound specifically with respect to these graphs and not some other graphs that we are able to construct? What is so special about this construction of Burling graphs? So perhaps there is something special about them, so I will maybe try to convince you during the second part of my talk that they have some interesting properties which other constructions do not have. But still, asking for a class to be B-bounded, at first sight, it looks like a difficult thing, like a strange thing to do. Okay. Anyway, there is this conjecture which was raised by Chudnovsky, Scott, and Seymour in 2021, which is a weakening of Scott's conjecture. Instead of asking for the class to be chi-bounded, we just ask to be bounded. Okay? So for every f, for every graph f, the class of f subdivision free graphs is B-bounded. So I guess the motivation for this conjecture was just that we didn't know about any other construction which would disprove Scott's conjecture. But still, they write in the paper, quote, "We have little faith in this conjecture." So it may have been asked as one of those provocative conjectures, like, for example, that every chi-bounded class of graphs is polynomially chi-bounded. Okay, like nobody believed that to be true. Now we know it is not true, but it was still considered to be a conjecture. However, it turns out that this conjecture is actually quite likely to be true, and the main result of this work is that it is true for maybe perhaps not yet in general, but for quite broad classes of graphs which are F subdivision free, in particular for string graphs. And it's also true, for example, for classes of graphs with bounded asymptotic dimension. I don't want to define what that is, but if you know what that is, then they actually are also B-bounded. And like most generally for this result, this conjecture turns out to be true for classes of graphs which are F subdivision free and 2 controlled, which is one more assumption, like one more condition, which I'm going to define now. So what does it mean for a class to be 2 controlled, or more generally R controlled for some integer R? A class of graphs is R controlled if there is a function, let's call it G, such that for every graph in the class we have the following inequality. The chromatic number of G is bounded by the maximum over all vertices by the function G of the maximum over all vertices, maximum chromatic number of a ball of radius R centered at that vertex. Okay, so we take ball in G, C radius R. So this is also some kind of a witness for large chromatic number, but it's no longer a bounded size witness because these balls can have arbitrary size. So like this condition is, in that sense, it is much weaker than the condition of being B-bounded. Maybe let me digress for a moment and show you why this bounded size is something that can be considered interesting. So there is a well-known open problem in computational complexity theory, which is called chromatic number approximation. This is a promise problem. We are given two parameters, k and l, with the property that k is like with this inequality. And on the input, we are given a graph which is promised to satisfy either that the chromatic number is at most k, or the chromatic number is strictly greater than L. And the goal is to distinguish whether this or this holds. Okay, so we want to answer yes in this case and no in this case. So for k equal to L, this is just the traditional k coloring problem, which is known to be NP-complete. And the conjecture is that this problem is NP-complete or NP-hard for any choice of k and L, well, as long as k is at least 3, of course, because otherwise it's trivial polynomial type solver. It is known to be NP-hard for some choices of k and L, but still such choices where this gap in between is not too large. Okay? So now, say that we further restrict our input graphs G to some class of graphs, which is, say, chi-bounded or B-bounded. Then, if we take L equal to f of k, or f of k in this other case, so if we take L sufficiently large, then chi-boundedness or B-boundedness gives us an algorithm to distinguish this case from this case. Yes, because if the clique number, say, okay, how to distinguish that? We just, for example, for chi-bounded, we just check whether there is a clique of size greater than k or not. If there is a clique of size greater than k, then we must be in this case. We cannot be here. Yes. Otherwise, if the clique number is at most k, then chi-boundedness gives us that the chromatic number is at most f of k, which means that we cannot be in this case, so we are in that case. And the same for B-boundedness. However, if we want to exhaustively check the condition whether there exists a clique or whether there exists a copy of BK, just by checking every possible place where this copy could sit, then it has to be of bounded size. Yes? So this is why that bounded size matters, because that gives us quite trivial algorithm to solve this problem for those specific classes of graphs. Okay, so that's it about chromatic number approximation. So let's go back to this notion of R control. So we can write the following sequence of implications. One notion that we have is chi-bounded, and it turns out to be equivalent to one controlled. That's not difficult to see that they are equivalent. One way is trivial, and another way, the other way is a simple induction on the clique number. Let me just skip that. It's not that important. Then a weaker notion is that B-boundedness, and then yet a weaker notion is two control. The reason why we have this implication is because those Burling graphs and induced subgraphs of those Burling graphs, they turn out to be two controlled. We will have even a stronger statement in a moment that all string graphs are two controlled. So in particular, all Burling graphs and induced subgraphs of Burling graphs. Therefore, if we can find a large Burling graph in our graph, then because like large Burling graphs contain the large poles of radius 2, large in the sense of chromatic number, then we know that if the chromatic number is large, we can find a large pole of radius 2. And so on. And yet we have, for example, R controlled for some, right here, R controlled for some R. So Chudnovsky, Scott, and Seymour in this paper, they proved the following two results. First of all, the class of string graphs is two-controlled. So in particular, Burling graphs are two-controlled too, because they are string graphs. And second, they proved that for every R and for every F, if the class of F maybe let me write it this way. For every R controlled for every R and every F, every R controlled class of F subdivision three graphs is two-controlled. So when we are excluding induced subdivisions of some graph, then two-controlled and R-controlled for whatever R, they turn out to be equivalent. Of course, except for one controlled, which is strong. Okay, so like these two notions collapse for F subdivision 3 classes of graphs. We don't know what happens in general. So I don't know of any hereditary class of graphs which would be R-controlled for some R, but not two-controlled. And our main result is that actually for F subdivision 3... Sorry?
Are greater equal to here, or?
For R equal to 1, this implication also holds, because then this is stronger than this.
It's implication. Oh.
It's implication.
It's implication.
Yes. So the main result is that this like collapsed notion for F subdivision 3 graphs also collapses with P bounded. They are all the same. So let me write our result is that actually I am going to exclude not just all subdivisions of some fixed graph F, but let's take KTT and I just want to exclude one subdivisions. It's enough to exclude one subdivisions. So for every T, every two-controlled class of KTT1 3 graphs is B bounded. Okay? So just to recall what it means, if we have a graph from a two-controlled class of K1 TT3 KTT1 3 graphs, and the chromatic number is large enough, then this is witnessed either by a large clique or by an induced copy of large Burling graph. Okay, large clique. So this in particular applies to string graphs because string graphs are two-controlled and they they are K3313. Yes, this is that observation by Zimmerman. And it's already actually interesting for the class of induced subgraphs of Burling graphs. It's already on tree. Okay? So corollary, let me just write this one, corollary, the class of string graphs is bounded. So now, what remains to prove this conjecture? It just remains, like in view of this result, it just remains to prove that whenever we have a class of F subdivision free graphs, then it's two-controlled. Or just that it's R-controlled for some R. And this has been conjectured by Scott and Seymour in 2020, namely for every F, the class of F subdivision free graphs is two controlled. And now we know that this conjecture is equivalent to this conjecture. Okay? Yes, so I think that will be it for the first part of my talk concerning Scott conjecture and the relatives of Scott conjecture. Do you have any questions about this?
Maybe a silly one. So there is a difference between one controlled and two controlled. Do you have any easy example?
Burling graphs. But it's not. Yeah, one controlled is the same as chi-bounded. So yeah. Anything that is two controlled but not chi-bounded, it is not one controlled. Yes.
So these other classical constructions, are they controlled when they are?
Yeah, so that's an interesting question. So, okay, I said that in general, I don't think whether, I don't know whether this is a proper implication, but we don't know whether any of these, okay, this we, of course is not a, this of course is a proper implication, but this I don't know either, whether it's a proper implication. It might happen that every two-controlled class of graphs is unbounded. I think a good candidate for a counterexample is a class of twin-cut graphs, which is kind of similar to Burling graphs in some respect, in some aspects, but I'm not sure whether they are known to be two-controlled. I think they are known to not contain arbitrary large Burling graphs. So, like, starting from some point, that the Burling graphs are not induced subgraphs of twin-cut graphs. Like, I believe that's the case.
Is there no separation between two-controlled and three-controlled?
No, like, I don't know of any separation.
And top graphs, are they controlled or something?
No. They are not, because they contain graphs with arbitrarily large chromatic number and arbitrarily large girth. So they are not controlled for any R.
Michelsky graphs?
Michelsky graphs contain all triangle-free graphs. So they are not controlled either.
Just graphs?
I don't know. I don't want to say anything stupid, so let me just say that I don't know.
Nice.
Okay, so let me proceed with the second part of my talk. Maybe I will make some space erasing this thing. So I want to tell you more about specifically Burling graphs, how I define them, how we can define them in other ways. So first, let's do this construction of B1, B2, and so on. And I want to define these graphs in terms of two operations which work on graphs with a marked independent set. So they are these are operations which not transform just a graph into another graph, but graph with a marked independent set of vertices into another graph with a marked independent set of vertices. Okay? So B1, it will be just this. Okay? Maybe I'm not sure how this is well visible. Maybe let me use this orange. It should be better. So this is the marked vertex, okay, in B1. And now I want to define two operations which will help me defining bk plus 1 from bk. One operation is called clone, and it works as follows. We take some graph with a marked independent set, and we pick one of the marked vertices here. This is this thing here is the neighborhood of that vertex V, and we are transforming it in the following way. So I'm duplicating this vertex. One copy will be marked, another will be not unmarked. And then I'm also adding a marked vertex adjacent just to this one. Okay, this is a clone of this vertex V in such a way. And another operation, let's call it substitute. So in this operation, we have a graph with a marked vertex. Again, let's call it V. And we have another graph, but in this other graph, we just consider all marked vertices together. Okay, so these are now all marked vertices in this other copy. So I'm taking two graphs which can be constructed in some way using these operations, this and this one, and now the result is going to be defined from both these graphs. So it's just looks as follows, namely, we substitute these marked vertices for this one. So we get something like this. Okay? So this original neighborhood of V, it becomes additionally the neighborhood of each of these vertices. So those vertices have their own neighborhoods on the right side, and that's preserved. But we also add this neighborhood of V as a common neighborhood of these vertices. Okay? So now, using these two operations, let me define bk plus 1 starting from bk.
So this graph on the left side of the substitution could have other marked vertices.
Yes, there may be other marked vertices here. There may be other marked vertices here. Nothing changes, but there are no other marked vertices on this side. We do all of them. Okay? Notice that these two operations preserve the fact that the marked vertices form an independent set. And they also maintain the property that the graph is triangle-free. Yes, starting from the triangle-free graph, we keep the property that the graphs are triangle-free just because of the way how we introduce additional edges. We always connect to a set of marked vertices, therefore, since they are independent set, we cannot create Okay, so we take BK, and let me just, for the purpose of the example, let me just assume that it has two marked vertices because it will be easier to draw the example this way. The first set, second set of vertices, and the rest of BK. Okay. And also for each of these marked vertices, we take another copy of BK, which again has these marked vertices here. So first, in each of these copies, I'm going to clone each of the marked vertices. This is phase one of the construction. So we clone this. We clone each of these vertices one after another, and then we substitute that for this vertex and that for this vertex. Okay. So this and this, and whatever we obtain with our BK plus 1. Okay. So because these operations preserve that the graph is triangle free, it is triangle free. What's the property about the chromatic number of the graph? Here it is. For every proper color of the non-active vertices of BK, there is an active vertex V with the property that if we look at the neighborhood of that V, then we see at least K colors on the neighborhood. Okay, this is a proper coloring with any number of colors, no bound. Okay, and if we have it in BK, then we will find a neighborhood with at least K colors. So let's see that this holds. It trivially holds here. Yes, for every coloring of that, there is a V with at least one color in the neighborhood. So now suppose that it holds for BK. So in particular, we have it for that. Like we have a coloring of the non-active vertices of BK, and those non-active vertices of BK, they come from this copy or from this copy or from this copy. Yes. So first we look at the coloring of the non-active vertices here, and by this property, there is an active vertex, like for example, this original V that was here, such that on this neighborhood we see K colors. At least K colors. Yes. So now what happens inside this copy of BK? Again, there is an active vertex, say this one, or B prime, so that if we look at this neighborhood, then we see at least K colors. Now there are two cases. If these K colors are different from these K colors, then this vertex, this active vertex, already sees at least K plus 1 colors. If they are exactly the same sets of K colors, then now this vertex, which is a clone of that but non-active, it sees that set of K colors here. Therefore, this active vertex, okay, therefore, in that proper coloring which we have here, it has to have a different color from this set of K colors. So this one has a different color. But now we have assumed that this vertex also sees that specific set of k colors, which is now equal to, assumed to be equal to that set of k colors. So it sees at least k plus 1 colors. Okay? Yes, so that property in particular implies that the chromatic number of bk is at least k plus 1, because in a proper coloring we also have a color for v, which is different from these k colors. And the fact that it's at most k plus 1, you can just follow the construction and color the vertices in the most straightforward way. And k plus 1 colors will suffice. Okay, so this is the construction of the sequence. And okay, like, let's relate it to those theorems that we see. At first sight, nothing special about this construction. It's just one of these inductive constructions of graphs with large chromatic number, which are triangle-free. Yes. So, but then it turns out that these Burling graphs have some interesting properties. So first of all, let me make this definition. Say that the class of graphs B, which is called Burling graphs. This is the definition due to Burling and Trottignon from recent years. That this is a class of induced subgraphs of BK for any. Okay. Yes, so we take all the graphs BK and close it under taking induced subgraphs, and we obtain this way a hereditary class of graphs, which following Burling and Trottignon, which we call Burling graphs. Okay, so we know that these graphs are triangle-free. We know that they have arbitrary large chromatic number. They also have arbitrary large fractional chromatic number. They turn out to have a bounded whole ratio, which means that they always have linear size independent sets. It's a nice property which somehow contrasts unbounded fractional chromatic number. That's a yet unpublished result by Rigo and myself, but like the proof is induction. It's not anything complicated. What else? They have nice equivalent characterizations, like this paper by Burling and Trottignon. It provides a lot of equivalent characterizations of these graphs. My favorite one is that they can be characterized as intersection graphs of rectangular frames. So intersection graphs of boundaries of rectangles. By boundaries, I mean that nested frames, they don't generate an intersection. Every intersection is supposed to look like this, so and specifically directed this way to the right. So every intersection looks like this. And there are 3 forbidden configurations, namely this one, and this one. This is actually a triangle. The only way to get a triangle is this restriction. Okay, so these are excluded configurations. So the class of graphs having this kind of representation is exactly the class of Burling graphs. That's turned out to be the case. Okay, but now if we look at these two operations, clone and substitute, then we can also say that the class of Burling graphs is the closure of this under clone and substitute. Is that clear? Yes, so first of all, like the construction of BK is made using clone and substitute, so one direction is clear. But also, like within this construction, we can see just clone or just substitute. Yes, suppose that we want to do a clone, then it's here. Yes, we just forget about anything else. We see the clone just here. And if we want to do a substitute, okay, we take a specific vertex V, we forget about this part, and we also forget about these clones. We just pick the original active vertices here, and then we just get a substitute. Okay, so we can recover clone and we can recover substitute within that construction. Okay, what else? This class of graphs is recognizable in polynomial time. This is a result by Paweł Żążewski and myself recently on arXiv. We also provide a polynomial time algorithm for the independent set problem. And I believe this is the first known hereditary class of graphs, which is recognizable in polynomial time, polynomial independent set algorithm, but is not chi-bounded. Okay. And now, given that this class of graphs, we can use it for that result because it is a subclass of string graphs. So Burling graphs are B-bounded. That's a corollary to this. So that implies that they form a minimal hereditary class of graphs which is not chi-bounded. Whatever we remove from that class of graphs, if it's supposed to be hereditary, it means that we actually remove some bk, because whatever we removed must be an induced subgraph of some bk. So we also remove all bk's starting from some k. And then the chromatic number is bounded by this condition. Yes, by the definition of being B-bounded. This is just 2. This is bounded, so the chromatic number is bounded. So again, to my knowledge, this is the first known hereditary class of graphs which is not chi-bounded and is minimal with that property. Yes, of course, we know that every chi-bounded class of graphs contains some minimal chi-bounded class of graphs. Actually, is it true? I'm not sure this is true. If we take intersections of subclasses, which are each of them may have a different function, so that's actually not necessarily true that every class of graphs which is not chi-bounded contains some minimal one. Okay, anyway, I don't know of any other minimal one than this one. Okay, so an important ingredient of this result, which is here, is that we have yet a different way of constructing that class of graphs B, which also can be expressed in terms of these two composition of these two operations, but a simpler composition, much simpler than this one. And then it makes it really useful for so-called Chudnovsky Seymour framework, which I will be speaking about in the third part of my talk. Okay, so let me define this operation. I'm going to call it double. So again, we have two graphs with marked independent sets. This is the first one. There is a marked vertex V, and maybe there are other marked vertices here. And there is another one for which I'm now taking all marked vertices. And this marked vertex, like there are no other marked vertices inside here. So what is this double? Like, what's the result of this double? First of all, I'm doing a clone of that vertex V. So if there is this vertex V here, then this is just a clone of V. And then I want to substitute this for that vertex. So what does it mean? It means that instead of this one, we are getting these edges here. And that's it. This is the double operation. And it turns out that the class of Burling graphs can also be obtained from this one using just the doubling operation. And this is not trivial. For example, you may say, wait a moment, this has a cut vertex. Cut vertex should not make the chromatic number grow. Yes, like a consequence of that is that if the chromatic number, that this operation makes the chromatic number grow, yes? But cut vertices don't make the chromatic number grow. However, notice that, okay, when we do one iteration, then this is a cut vertex. But now consider what happens if this whole graph appears as the right one in the next step of the construction. We get a connection to both these active vertices and to those active vertices, so that will no longer be a cut vertex. Okay, so in one step, okay, we create cut vertices, but they are no longer cut vertices in further iterations. Okay, so how to do this? How to see that this doubling operation also creates like all Burling graphs? One way, again, we constructed this using clones and substitute.
Sorry, when you say that you obtain all Burling, it's as induced subgraphs?
Yes, as induced subgraphs. Thank you. Thank you. And also here, I forgot to say that using the closure of B1 under clone and substitute and taking induced subgraphs. Yes? And here the same. We close B1 under doubling and taking induced subgraphs, and that gives us the class of Burling graphs with those additional marked vertices. Okay, so like the way to show that they are equal is now like as we had before. We need to recover the clone and substitute just within that operation. And clone is easy. We see it here. Yes, we just take one of these vertices and forget about the rest. That's clone. But substitute is more tricky. And actually, what we need to do if we want to do a substitute, to see how to do the substitute using left graph and right graph, then we need to look at the entire construction sequence of the left graph using the doubling operations and modify that construction sequence by doing the substitute with the right graph at every step of the construction sequence. Okay? So perhaps let me show you like one case of that. Okay, trivially the base case is that if we have B1 and now we want to do a substitute, which then this means, yes, this is a substitute of B1 and something. And this we can recover here. Yes, that's what we see here. Actually, for the purpose of the induction, we need something slightly stronger. We also need to preserve, in a sense, an original copy of that. So I need to have an additionally this vertex. But this is also I can do, because first I can take my right graph and add an independent vertex to it. This is, we recover it here. Yes, just forget about this part, forget about that part. We have our graph plus one additional vertex. And then we do this substitute of this larger graph for B1. Okay? So then we have a step in our construction of this yes, we have this doubling step. show. So we start with, let me draw it this way. And we turn it into this graph. Another copy here. And this is here. This other copy. Yes, this is a step of the doubling construction. So now I want to do a substitution where for some vertex v, yes, we have this substitution step with some right part and with a marked vertex v on the left part. So this is now the right part. And now, and actually I don't want to just do the substitution, I want to do the substitution with this, like this additional vertex here. And now the question is where the vertex v is. Let's suppose that now the vertex v for which we want to substitute is one of these. So it has its neighborhood here. Maybe let me draw it this way. We have the vertex v, which has some neighborhood here. And that edge goes to v. And this is our vertex v. So the substitution operation which we want to do is we want to forget about this v, and I want to direct whatever this v was connected to, I want to connect with all these vertices. So this is the result which we want to obtain. So how to obtain it? Like the assumption is, and also here. So the assumption is that I can obtain this here. So this is our v. Yes. This is our left part with this additional vertex. And what we actually, the assumption is that we were able to do this just on that part of the graph. So now, what now remains to do from this and this guy is to do the doubling operation of that vertex. Yes, which creates a copy here. And this copy will be connected to every active vertex on that part. So to these active vertices, and this one. And let's see that this is exactly what we want here. Okay? So this was the case that the vertex v was on this part, like in this lower graph. The other case is that the vertex v is here. Yes, the vertex v for which we are substituting is here. Then the result of the substitution which we want to obtain is simpler. Okay, here also one of the vertices inside. But like this is the most interesting case. So now the result of the substitution which we want to obtain looks like that. Okay, so this is unchanged. We have our v, but now we have those marked vertices and this one. Yes, this is what we want to obtain at the end. But now our assumption is that just looking at the upper part, we can substitute for that vertex. So what we can obtain is we can obtain this thing. And now, okay, and this is so far the lower part, they are not yet connected. So now we do the double of that additional vertex. This is why we need that additional vertex. But for this specific step, I need to double that vertex to create this one. Yes, which is this one. Okay, so that was the proof that that was the proof that it's just enough to do this doubling operation to get our Burling graphs. So this in particular means that now we can consider, like, okay, if we want to have a sequence, now I want to have a sequence of graphs which will contain all, the BK will appear as an induced subgraph at some step, and still the sequence will be constructed in such a way that every graph in the sequence is obtained by doubling the previous one with respect to some vertex. Yes, so by this operation we can do that. Yes, so we can start with, say, D1, which is equal to D1, and then get D2, D3, D4, and so on. Each of them is obtained by doubling the previous one. I can assume that in this doubling, we are taking copies of the same graph. Like for the doubling operation here, I was not assuming that when defining the operation. It could have been a different graph here and here. But then if there is some construction sequence which leads to a construction of this graph and some other construction sequence which leads to a construction of this graph, then I can compose these two construction sequences to get a sequence that constructs a larger graph which contains both this one and this one as induced subgraphs. And then I can use this larger one to double it with itself to get the next step in that construction. Yes?
In this doubling operation, you have to do some choose of the mark.
Yes, it is important how we choose the marked vertices. I think it is just enough to assume that every vertex at some point gets involved in the operation. That there is no vertex which will constantly remain not chosen, until the end of the sequence. But also we can just use the fact that each BK can be constructed using some sequence and just compose these sequences together. Okay, so maybe the details need to be worked out, but I guess it's quite natural that I can get such a sequence which will contain every BK at some point. Okay, so let's fix such a sequence, and that will be important for the last part of my talk, which is going to be the actual proof of this result. Yes, this is the most important here. And I'm going to use this sequence for the proof. Okay. And the proof uses what I would like to call the Chudnovsky-Scott-Seymour framework, which is extremely powerful proof method for this for this kind of statements, that assuming that we have a chromatic number large enough in some two-controlled class of graphs, then we can find something. And it was developed in two papers. Like the first version of that framework was in the paper about long holes, so which is that if we exclude sufficiently long cycles, then the class of graphs is chi-bounded. That's a paper from 2017. And then the other paper is this 2021 paper here, where they also developed this framework, where they were able to find, assuming that they have a graphs with two controlled class and excluding this kind of subdivisions, they were able to find, and with high chromatic number, they were able to find some specific graphs, but which are some kind of forests of lumps, this is how they called it, which are like specific induced subgraphs of Burling graphs, but quite restricted induced subgraphs. So we do this like in full generality. We extract as much as is possible, because actually we can apply this result to the class of Burling graphs itself. So we cannot, if the chromatic number is large, we cannot find anything else than a clique or a Burling graph. Okay? Yes, so that's the third part of my talk. Chudnovsky, Scott, Seymour framework. So we are working with a class of graphs which is two-controlled, and the proofs usually look like this. Assume that we have a huge chromatic number, where at the very end we learn how huge this huge should be. Yes? And using this sufficiently large chromatic number, we want to find some structure which also in some, there will be some pieces with large chromatic number. And now this large that we started from is a function of that large that we want inside these pieces. Okay? And one more standard trick that we do is that, like, in the whole proof, we do induction on the clique number. Yes? So like we want to find a large clique or a large Burling graph. So okay, we will either find a large Burling graph or we will find a k-clique, but assuming that we can find a large Burling graph or we can find a k-1 clique. How is it useful to do this induction? Then we know that if we take a vertex and look at the first neighborhood of that vertex, then its clique number is less by 1. Therefore, it will have bounded chromatic number, or we will find a large Burling graph already here. Okay. So we are two-controlled. Then if we have a graph which has huge chromatic number, two-controlled gives us a vertex V such that a ball of radius 2 centered at this vertex has huge chromatic number. But now, since we are doing this induction, we know that actually the ball of radius 1, which is just V plus the neighborhood, this has small chromatic number. So we know that large chromatic number is here. The vertices at distance exactly 2. Okay? So what we are going to do in our graph with large chromatic number, we extract this vertex V. Here we have this first neighborhood, and here we have this second neighborhood, which still has huge chromatic number. So we repeat. Okay? Again, we extract the vertex, first neighborhood, and second neighborhood has huge chromatic number, and so on. We repeat this some bounded number of times, but again, the bound will be huge, and it will depend on like the parameters that we want.
What is the setup? You assume that it's two-controlled, or you?
We are assuming that it's two-controlled.
Okay.
We are assuming that it's also KTT K1 free. So this is like subdivision of KTT1 is something that we will find at some point. By the way, one thing that I forgot to tell you is that if we have a class of graphs which is F subdivision free for some F, then it is KTT1 free for some T. Because if we have large 1 subdivisions of KTT, then we can construct like 3 subdivisions of any graph. How do we do it? On the left side, we take the original vertices, and then we use the right side and these subdivided edges to route paths of length 4 between selected pairs of vertices. Yes, and that builds our 3 subdivision of any graph we want. Okay, so if we are F subdivision free, then we are KTT1 free for something.
So, okay, so you assume that you're too controlled, and now you assume that you have a huge chromatic number.
Yes,
and
we are
as a
assuming
result,
that we have a huge chromatic number,
as a
the
result,
clique number is bounded,
and the clique number is bounded.
and also the first neighborhoods are bounded, have bounded chromatic number.
Yes.
Yes, because we are already inside induction.
Yes.
And what we want to find is we want to find either large dk, which we know that it will contain a large bk for some other k. Yes. Now we take this dk, or we want to find the large ktt1 as induced subgroups.
Okay, so this huge is a function of k and t, yes?
And t and the clique number.
And the clique number that you take.
Yes. And also this function g, which defines our control. Yes.
Yes.
Because this is used in every step here.
Yes.
Okay, so let's go back to this construction. I'm doing this kind of multiple extraction of these first neighborhoods. And what we obtain, so this way is something that is called a multi-cover. Okay, so here there is something that is still large in the sense of chromatic number. Yes, large will always mean large chromatic number. And it is covered by each of these neighborhoods, which means that every vertex here has a neighbor here, has a neighbor here, and so on. And moreover, these top vertices here, they have no forward edges. No edges to anything that is here. They may, and they usually will have backward edges. In particular, for this construction, we know that each of these vertices also has a neighbor here, here, and here. But for this term multi-cover, we don't require this last condition. Because actually in the process, when working with these multi-covers, sometimes we will be restricting these sets to smaller subsets. And we still want them to cover this, which also can get restricted to a smaller subset, but we can lose these connections. And actually, in some cases, it's profitable if we lose these connections. So they are two specific additional conditions which we can.
But if you restrict something on the left side, you must drop the equivalent on the right side.
Yes, yes.
Okay.
There will be some very specific process in which we restrict. It's not, we don't do it mindless, like it will be very specific. So let me first define what it means that we have an independent multi-cover. It's a multi-cover like this love set here is still covered by each of that. But now, in addition to the property that those vertices have no forward edges, we also require that they have no backward edges to this case. Then we call this such a multi-cover independent. And now, Chudnovsky, Scott, and Seymour, they proved that large independent multi-cover implies KTT1 as an induced sum. They can find it. And I don't want to explain how this is done because it's not complicated. I mean, it's not simple. It's complicated argument. But like it's all in that paper. We don't introduce anything new here. It's just a tool that we can use whenever we want. Okay? So then there is this other term, skew multi-cover, which is in some sense the other extreme. Again, we have something like that. But now we require, okay, we still require that we don't have those forward edges as before. But now here, backwards, we have everything. Okay, this is the other extreme, and this is called skew. And the core of the argument is working with skew multicovers. But before proceeding to that, I need to show you how we can actually get anything like a long independent multicover all along skewed multicover. Because like this is the first part of this framework, that we can get either this or that. So what actually happens when we do this process is that in each step of the process, we do some additional cleaning. So suppose that we have constructed this multicover up to some point, and now we are about to continue constructing that multicover. But what we are going to do at every step is that we will appropriately restrict this thing so that the chromatic number is still large. And also we will restrict these guys in such a way that they still cover like this smaller thing here. You will see later what appropriately means. And then we are going to apply the two controlled condition plus induction. So then we get this. And then we again do this restriction. So for now, I will tell you later what is this step here. It's too early to say it now, but now let's focus on this step after we extracted this guy. What is the goal? The goal is to maintain the property that each pair of these covering triangles here is either independent or skew. But for different pairs, it may be different condition. Why is it interesting? Because if at the end we get such a long multicover where every pair is either independent or skew, then we can apply Ramsey theorem to get along fully independent or to get along fully skew. And then we end up either in this case or in this case. Okay. So now, we have extracted this, and here we have this specific vertex V. So I can partition each of these guys into neighbors of V and non-neighbors of V. Okay? Say that we can even denote them. Say that non-neighbors we marked 0, neighbors we marked 1. This is part 0, this is part 1, and so on and so on. So now every vertex here, after this extraction, it has a neighbor here, it has a neighbor here, it has a neighbor here, it has a neighbor here. So we just write a string of zeros and ones saying whether this neighbor is in this part or in this part, except that we want to prefer part 0. We want to prefer non-neighbors. So if we can write 0, then we do. Otherwise, when all neighbors are in this part 1, then we write 1. Okay? So this is a coloring of that with a bounded number of colors, not a proper coloring, just a partition into bounded number of parts. So if this had a large chromatic number, then one of the parts will have large chromatic number, but will have all the same string. Yes? So we just restrict to that part, for which that string is homogeneous, say 0, 1, 0, 1. And then we just kept these parts, yes? So here we keep 0, here we keep 1, here we keep 0, here we keep 1, and that will be our extended multicover. And now we have the property that this, with respect to each of them, is either independent or skew. Like the previous pairs we already had by induction, that they are either independent or skew, and we don't lose this condition when doing these restrictions. Okay, so this way we obtain pairs which are like all pairs are independent or all pairs are skew, so that afterwards we can apply Ramsey theorem to select a subset which will be all independent or all skew. If we get a subset all independent, we apply this to extract KTT1. If we want a long which is all skew, we want to find this thing. So actually, how long skew subset we want? As long as the index that we want to find. So like if we want to find index k, then we want to have a skew sequence of length k. Okay. This is all skew, but this is also taken as a subset of something much larger. You should remember that there is something much larger.
So you have this preference. So if there is a skew, then you know that there was no edge to the zero part that you removed.
Yes, I'm afraid I will not be able to explain you why this preference is interesting, because this is something that we needed to, in particular, to obtain the induced, those decays as induced subgraphs. I only have time to show you why we can obtain them as homomorphic images, because there is just one more step to do to obtain them as homomorphic images. And notice that homomorphic images, they are still bounded size witnesses of large chromatic number, because the homomorphic image of decay, it also has chromatic number at least k plus 1. But for homomorphic images, I don't need to care about non-edges. I don't need to guarantee non-edges. I just need to guarantee edges. So for that, skew condition is nice because it guarantees me a lot of edges. Okay, so we have something like this, which is a subset somewhere here. We should always keep remember. So now we have this construction of decay by doubling. And we are going to, and we have this construction as we were extracting those couples one after another. And now I want to proceed backwards in this construction. Okay? So the induction statement is that, say, at some point, say here, the induction statement is that inside that part, I can find a copy of DI, homomorphic copy now. In general, it will be an induced copy, but now let's focus just on a homomorphic copy. But such that, okay, the non-active vertices are here, and the active vertices can be chosen from here, or they can be chosen from here, a complete separate copy of all active vertices, and so on. Yes, in each of these covering sets, I have a separate copy of active vertices. Yes, so if I have active vertices V1, V2, V3, then there is a copy of V1, V2, V3 here, and a copy of V1, V2, V3 here, and on each of these previous steps. And I want to maintain, okay, if this is DI, and I want to construct the DN at the very end, then I need N minus I more steps. Okay, so let's try to back up one step. What I would like to do Okay, so there is this doubling procedure. So we have a vertex V, and the left copy here is the one that has been found by induction. So in particular, one of those vertices V is a copy of V inside this neighboring sets, and it is connected to its neighborhood here. So what I would like to do is I would like to make this copy of V to use it as this non-active vertex, because when going one step back in the construction, I just want to have copies of active vertices here, yes? I don't want any more vertices here. So now I can treat this copy as the new non-active vertex, the cloned one. So that will be the other V, but still, I need to get this whole thing as a homomorphic image, yes? So the non-active vertices of that, okay, let me use L. The non-active vertices of that, they can be anywhere here, but the active vertices, I should be able to provide them, like perhaps some other copies of, yes, now I mean these. Now I mean these active vertices. I should again have their own copies here, 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 and here, and they all should be adjacent to V.
By non-active on the right, you mean those on the right?
Yes,
side
this is the right part,
Uh-huh.
right non-active part. So I want to find it somewhere here.
But then if you use so many vertices, like on your figure to the left, then and you just make one step, so you wanted to have some space for the next steps. And minus I you wrote, and you make just one step now, and you use everything.
No, I just used one step. So like
you use one step, but then the active vertices will be spread out on all the things.
Yeah, but this is the condition that I want to maintain. Yes, I said that the inductive condition is that there are non-active vertices of Di are here, and the copies of active vertices, they are supposed to be everywhere here. Here one copy, here another copy, here another copy, here another copy. So this is what I need to maintain this condition, that I will have one copy here of this purple active, one copy here, one copy here, one copy here, and one copy here. Because then, in total, I have one copy of the new active vertices here, which is the union of orange and purple. Yes? Yes, for this Di plus 1, yes, this plus this, together it forms Di plus 1. And the active vertices of Di plus 1, they are the orange vertices, including V, plus the purple vertices. They are all the active vertices of Di plus 1. So I want to be able to find them everywhere.
And so you cannot map them on the same vertices because they have a kind of different.
For homomorphic image, I can map them onto the same vertices.
But,
they can coincide.
Or purple are neighboring with this special white vertex, and orange.
For homomorphic image, I don't care of non-neighborhood.
I see.
Okay, so this simplifies stuff a lot.
Okay.
Okay, anyway, this is the problem, that how to find this whole thing, that there is this vertex V and these neighbors, and such that, like, this whole thing, together with each copy of these neighbors, it forms again a copy of Di. Why do we have anything like that? So that's the beauty of this framework, that we actually get it for free, assuming that we have done, when doing this extraction, we have done appropriately this step. So what do we do during this extraction in that step, before extracting the new thing? We anticipate that we will be doing this back step for that specific index I, which means that we are going to iterate over all possible indices I. So let's fix an index I. Then we anticipate that these previous parts of the cover will be a specific subset of whatever we see here. Because before doing Ramsey, we don't know what subset it is, but we can iterate over all subsets. Okay? So let's fix this, and let's fix a specific subset of I guys here. And now, that still happens before I did this extraction. For every vertex V, and for this I and for this specific subset, I'm asking a following question. Is there a copy of di anywhere here such that here there are non-active vertices of di, somewhere here? In these copies, each of these copies has its own separate copy of the active vertices of di. And these separate copies, they are neighbors of V. Like these four active vertices, they are neighbors of V. I'm getting an answer, yes or no? Yes, 1 or 0?
No, always no.
That will turn out to be impossible. But I'm getting an answer, yes or no? Okay? But we are iterating over all i's and over all subsets here. So I'm getting a vector of answers. This is again a vector of finite length. So I can homogenize this set with respect to like the most common outcome, most common in terms of the chromatic number. So there will be a outcome such that the number of vertices giving the same outcome the chromatic number of the vertices giving the same outcome is still large. So I'm just restricting to this. And after this restriction, I'm going to do that extraction of the new step.
But wait, you fix I, you fix subsets.
Well, the fix, I said I fix when I ask a single question. But when I asked multiple questions, it's iteration over all possible cases. Yes, so the vector is indexed by all possible choices of I and all I element subsets of the previous guys.
But then high chromatic number could be concentrated only on one value of I.
No.
Oh no, you get.
This is for every vertex, I get a vector of bounded length, and the coordinates of that vector are indexed by i's and by subsets.
Always the same answer. Okay. Wow.
And we are going like to restrict to a set which is homogeneous. So all answers the same. So now this was done with respect to a set which was homogeneous, in a set that was homogeneous. But now let's look what is happening here. Like, look at this vertex. This vertex is a witness that for that specific I and that specific choice of a subset, the answer is yes. Because we see, yes, this is whatever we obtain by induction. So if the answer is yes for that vertex, it must be also yes for that vertex, and this way we get this perturb thing. And this is the whole beauty of this framework. Okay, so things get more complicated if you want to get induced subgraphs, because we need to take care of non-edges, and we need to take care of the fact that for example, we could not use the same vertices many times, but like there are no more new ideas in our result compared to Chudnovsky's Seymour. It's still technical to get to induced copies. In particular, it uses something called clique multicovers rather than just multicovers. So we are constructing multicovers where the stuff here are cliques of bounded size rather than single vertices, because we need it for induction. One of the possible outcomes, one more possible outcome is that we will actually get a part of the multicover with this top clique larger by 1. So if that's outcome which we are constantly getting, then we will be able to construct a multicover with those clique larger by 1. But this has to finish because the clique number is bounded. Yes, so there are technicalities like that, but like the most important ideas, I guess, I was able to show you here. Thank you.